Oh, really? It's really the same. Oh, really? Cool. When you speak of
Okay, I think you
I don't know. You can hear me. Okay.
I think I want to make one announcement.
Sure.
Okay, I have a short announcement to make. For all those who won a code at the raffle, yeah, we forgot to mention that if you want to get the ebook, you should only choose the ebook, not the bundle, because there's two versions, only ebook and ebook plus printed version. And the code only works for the ebook one. So we'll also post this in the Telegram group. Thank you. Okay, now we will carry on with the talks. So we're having a talk on scientific computing for quantum technology. Yeah.
Thank you. Oops. Wait. Can you hear me? Can you hear me? Yeah. Okay. Thank you all. Can you all hear me? Yes. Great. Okay. I would like to thank the organizers for this opportunity, and thank you all for coming to this first talk of a session. My name is Nathan Shamma, and I'm a postdoctoral researcher at RIKEN, which is Japan Physical National Lab for Physics and Chemistry. Today I'm gonna introduce you to scientific computing for quantum technology. About myself, I'm a theoretical physicist working on the fundamental interaction of light with matter. And this research field is called cavity quantum electrodynamics, with regard to the interaction engineered in nanoscopic structures that can enhance the interaction and can really tune it in a way that is allowing us to obtain results in basic research and also in applications, as I will show. I'm one of the contributors of QTIP, which is the quantum toolbox in Python, which I will present shortly. And I also write a newsletter on quantum technology. Please check it out on Medium. It's medium.com/quantumtech. And I'm also involved from not the academic side, but from the technology transfer side in quantum technologies through a consulting company, Quantica. And if you have more information about this, please reach out after the talk. First, let me thank my scientific collaborators, Shanwaz Ahmed, who introduced me to open source computing, and unfortunately could not be here, but give me big help also with slides. And Dr. Neil Lambert, Frank Honori, and Simone De Liberato, and the research agencies that support our research. So, quantum technologies. This is a big umbrella name referring to actually a field of research that spans from quantum physics pouring into information science and also chemistry and engineering. What you see here are specific tasks in which quantum correlations are being engineered and tamed somehow in order to obtain and achieve some enhancement over current technological implementations. So these are not completely disconnected research fields, but this is a way of seeing the possible applications. Quantum computing would have applications that are very broad. The most immediate one could be for drug design by designing from a bottom-up specific chemicals or biological molecules. There is also applications to quantum communication, which is through the sharing of information that has some quantum correlations. And these are applications to cybersecurity. And then there are also other applications in sensing and simulations. I cannot delve in all of these applications. I will just give you an overview of what is possible in quantum mechanics. One application for sensing that is currently being looked into is actually for basic research. There are projects at LIGO to enhance the sensitivity of a detector of gravitational waves by using non-classical states of light. There are also studies in basic physics, because if we want to study phase transition, specifically phase transition that entails quantum particles, the best way to simulate it would be to have a quantum system that we can reprogram and engineer in order to study many different interesting properties of light and matter. And with regard to quantum communication, let me just mention that recently Chinese researchers have sent to space a satellite that shares correlated photons between distant objects on Earth and is able to, in this way, to perform quantum experiments. And this is a recent undertaking that is ongoing in China and all over the world. But before, I'm talking about quantum technologies, but what do I really mean by quantum? So let me just first say that in theoretical physics, we work with models and we try to simplify complex models. So at the basic constituents of matter can be seen as atoms, at least at low energy levels. And an atom can further be simplified into a system that has an electron down or an electron up, depending on the energy that it has acquired, depending on the state of the ground state of electron orbitals or the excited state of the orbital. And when the atom emits an excitation, it will emit a photon, and it will be de-excited. So this is already interesting because it gives a glimpse into what quantum really means. Quantum means nothing else than discrete, in chunks, something that is quantized, which is not continuous. And this is an intuition with regard to the quantization of the electromagnetic field that goes back to Einstein. And what we deal with are really quantum particles and discrete pieces of light and matter. So at the core, as you can see, this dichotomy of unexcited and excited of a two-level system, which embodies an atom or an artificial atom, really gives us the intuition to encode information onto this system, a 0 or a 1. This is embodiment of a bit. But this is a very special bit, because as this quantum system physically abides to the laws of quantum mechanics, also the information that is encoded into this bit abides to laws that are not those of classical information science, but of quantum information science. And a way to see this is the fact that if we take two quantum systems and we find a way to create some correlations between the bits, we are able to encode onto these bits more information that is possible classically. And one way of looking at this is by studying the superposition of this system and the entanglement properties of this system. And by measuring this system that is entangled at some stage, we actually perform a change on its state, and we really project it into one of the two possible outcomes. So this is another important piece of information, the fact that measuring something, it's like performing a calculation. And actually, these correlations were thought first, again, some really insightful work was performed by Einstein and his collaborators back in 1935. And only in 1964, John Bell understood that this correlation could actually be measured. And we could really distinguish between quantum and classical information and correlations. And more recently, experiments have been performed, especially in Alan Aspect laboratories. And back more than 20 years ago, Peter Shor had the intuition of using entanglement for information properties and for computational tasks. So here I'm just giving an approximate model of what is a quantum circuit, which starts with encoded information and some ancilla that then interacts with our entangled qubit, and then the two objects are measured. And this is a computation. And this is a way also to envision logical gates in quantum information. So this quantum information actually it's very flexible and can be encoded in many different systems that we can describe with this very rough approximation of a two-level system. They range from neutral atoms to charged atoms that have been stripped of a single electron, ions, from spins to photons. And even to macroscopic objects that are encoded into superconducting circuits, of which here you can see an image with an ant. So an important measure to see why we are at, for some measures, at a tipping point for quantum technology and for technological transfer, it's this plot, which shows, especially for superconducting circuits, how there's been a steady improvement over the capacities that we have in the lab of preserving these correlations. Over roughly 15 years, there's been an 8-fold increase of the time through which we can really preserve quantum information, entanglement in qubits, and also the capabilities that we have of reading this information and actually encoding this information with some degree of confidence, not probabilistically. And to be fair, superconducting circuits have really witnessed exponential improvement in their implementation as a platform for quantum information and quantum computing, as well as quantum simulation. But there, as I was mentioned before, there is a broad range of platforms that can be looked at. And without going into details now, maybe one can review these slides, but each system has currently some advantages and disadvantages, such as integration with CMOS technologies. And due to the technology transfer point is also highlighted by the fact that there is interest not only in basic research and research centers, but also by startups that are most often spin-offs of research groups, and also corporate players. And as you can see, superconducting circuits currently are leading in this race for quantum information processing and quantum computing. And here comes also open source, because here you see two articles. One is actually a Neurtu comment by the Google research group in Nature. Another one is a TechCrunch headline that both actually inside stress the fact of how open source is serving a purpose for the quantum computing platforms. Here I'm summarizing many of the quantum computing platforms available now and their respective libraries. These are all open source libraries, mostly written in Python. So what you're doing is you're coding and you're sending some instructions from the cloud to some actuator in a lab, which is performing a quantum experiment. So I would like to cool down a bit expectation for quantum computing in the short term. But what is really interesting in this research field is that it is really fundamentally changing the way research is being performed. Theorists like me can run a script, sending on the cloud, and actually this script is then transcribed into low-level code that can be compiled by the quantum compiler. And actually, this is a way of performing an experiment for a theorist from home. And this is something that has never happened in quantum research. So now let's get to QTIP, which is the library that I'm going to present to you. All those that I was showing before are quantum circuit simulator. And they're useful with an underlying quantum compiler or with a simulator of such compiler to really try to run these quantum scripts and quantum algorithms. Qtip is able to do this, to simulate these quantum algorithms, but also gives specific insight on the physics that governs also these machines. And why is that? Because there is an effort into explaining how noise affects quantum coherence and quantum computation. So these are just some of the many applications that for which Qtip is currently used by. These are topics that are of interest to the quantum research community. I will not go into details, but you can see even from the names and the pictures that the applications are quite broad. I think that Qtip has really three main strengths. One, that it serves its community. It created an environment, thanks to Python, in which a specific class, the quantum object class, it's basically used to do most of the work. And why is that? If we think at the Schrödinger equation, which I will show you shortly, which is one of the equations that explains at these energy levels most of quantum mechanics, well, that is just a linear equation in which, at least from far, you see a matrix multiplying a vector. And to some extent, quantum mechanics can be seen as linear algebra, matrix multiplying matrices. But then these matrices have some specific properties. And Qtip has some specific properties that are not found in most of the commonly available and excellent open source libraries in Python. For example, it is specifically engineered to deal with complex numbers, something that quantum mechanics researchers really deal about, really care for. Also, it implements non-commutative algebras, some underlying mathematical structures that are typical of quantum mechanics and that are used to describe measurements, interactions with different energies, and the evolution of quantum states. Moreover, there are some advanced mathematical techniques coming from statistical theory, quantum statistical theory, and quantum optics that are implemented in Qtip. So one can find very nice correlation functions, and instead of writing them from scratch, can really import them from Python. And then there is also the modularity point. That is the fact, as I will show, that different libraries or packages have been implemented into Qtip in an harmonious way. And finally, there is also some effort from the beginning, since from its creators, Paul Nation and Robert Johansson, into performing efficient calculations with these sparse matrices, also exploiting multiprocessing. Qtip was created around 2011 and 2012, and actually it was the evolution. It was inspired by MATLAB toolbox, and now we're at the 4.3 edition. I'm just one of the many developers that are working on Qtip. And as I said, many people worldwide are using it. And you also have to factor these numbers with the fact that we're talking of a very small community compared to the machine learning community, for example. It uses the BDS license, and it builds upon SciPy, NumPy, Cython, Matplotlib, and all of the other recent tools that have been developed in the Python ecosystem. As I said, it is both used in research, in education, also thanks to its visualization tools, and in industry by the same corporations and startups that are developing quantum hardware. So let me say why Qtip is so successful with a sketch. Quantum mechanics, it's famous for being hard. And it is true that even if now you're able to play with these excellent open source libraries that are available for cloud computing and quantum computing, quantum computing, you would basically be stuck after short. And why is that? Because one needs at first at least an intuition of what can be done. And Qtip is really good at this because it allows to really understand quantum mechanics. there's been a great effort by the developers of QTIP and which are basically the broader quantum optics community, into developing a lot of tutorials. And on the website, you can find over 60 of them with 20 quantum mechanics lectures. And we have just added some in July. This is just an example of a recent archive paper that appeared online in which a quantum experiment was performed with some neutral atoms that were entangled. And this was the first time that these kind of atoms were entangled. And these are actually lab data. And as you can see, this is an excerpt I took from one of the papers. They're citing the fact that they're using QTIP to simulate how noise is affecting their suboptimal signals that they observe in their data. This is just a map of the code, and here I'm just going to show you some of the visualization tools that we have that are ad hoc visualization tools for the quantum community, such as block sphere representation of a qubit, some correlation function of some state of light, and this also applies to quantum circuits, tomography of a quantum state, and also the option, something that I will spend few more words on, which is the implementation of topological circuits in quantum computing. And this is just an overview of what can be done with QTIP, which also includes optimal control of quantum systems. So here on the left, you're seeing some of the typical equations that quantum mechanics researchers play with, and on the left there are some encoding with QTIP. And again, the real power of it is leveraging on Python class structure. And a quantum object asks what kind of data it is, the type. If the matrix has some mathematical properties, what are the dimensions and the structure and the mathematical substructure of the system? Here are some other examples of how this is implemented. And let me just mention the fact that before I was talking about the Schrödinger equation. The Schrödinger equation, it's this equation that actually allows a unitary evolution, which means that time reversal is in principle possible, something kind of unintuitive in quantum mechanics. Why is that? Because there is no inclusion of dissipation and loss of information, if you want, of energy to the environment. So what QTIP is really good at, it's modeling realistic quantum system, which is also the quantum computing kind of systems that are being right now implemented in practice. And one typical equation, mathematical equation that is studied in this setting is the Lindblad master equation. I will not go into the detail, but I just want to point out some features of this equation. This part refers to dissipation due to noise. And as you can see here, ρ is actually the quantum state, the density matrix referring to all the information that you have about your quantum system. And then there is some operators acting on it. And as you can see, there are some operators acting from the left and then from the right, if you may. So a simple thing that QTIP does is just to convert this equation into a simple equation in a bigger space by tensoring these products, in which there is a bigger matrix multiplying a vector, and then exploiting the sparsity of this matrix, which contains the full dynamics. Some recent advancements in which I've been directly involved is the simulation of the dissipative dynamics of many identical qubits or quantum systems. And for these kind of problems, the scaling is very bad in principle. Even assuming that we can use this big approximation as the starting equation, you see that already for something roughly 15 or 20 quantum bits or quantum systems, we cannot simulate their dynamics with a computer anymore. But then we can look at this equation and we can see that the rate that actually affects each qubit, here there is a sum over all the number of qubits n, is the same for all the qubits. So even if this equation, what it says is that the system is dissipating, and each of its constituents can dissipate to a different environment, if we can permute any of the two-level system, any of the two objects, the dynamics should be the same. So we can take advantage of this permutational symmetry, and we can actually obtain an exponential reduction in the simulation of these dynamics. And this is something that we did with a library that I developed with Shanawaz Ahmed, and which has been inserted in QTIP as a module, the PIX library, a permutational invariant quantum solver. And again, the basic insight here is that we could exploit some symmetries that are typical of these specific algebras that are relative to quantum bits, but also want to stress the use of permutational symmetry and also of sparse and block diagonal matrices for the implementation of this computation. Of course, I'm just showing this without the pretense of explaining everything, but just also for some visual beauty. And here there is a plot just showing for a small number of qubits for which we could actually test our algorithm with existing algorithms in QTIP. You can really see roughly a 3 to 4 order reduction in computational resources and also in computing time. Why do we care so much about identical two-level systems interacting coherently and also dissipating or being driven by external energy? Well, because there is many processes that we can model this way. There is a collective excitation of energy, and I'm using very general terms because depending on what this two-level system encode, this could be electrical excitation or the interaction with a light field, and this could be spins or they could be atoms in an optical lattice. And finally, yes, let me also, so these are some of the applications that are possible with this new library, this new module in QTIP, which are dissipation-induced phase transition, out-of-equilibrium study of thermodynamics, a hot topic in this part of quantum physics, and also the study of emergent cooperative phenomena, something that we are familiar with also beyond quantum mechanics, as well as chaotic dynamics. And here is just an overview of some recent work that we did with this regard. From some part, reproducing known results in the literature that were not able to take into effect this local dissipation due to the computational complexity and overhead attached to this simulation, and also extending the previous results by looking into local incoherent terms affecting the dynamics of these systems. Here I just want to show another recent module that has been implemented, included in QTIP, which looks at how this quantum system can emit light into different waveguides. Another example of ongoing research is when there is, with an interesting encoding in mathematically, which is a hierarchical equation of motion implementation. It's basically when our system dissipates energies, but then somehow this information or this excitation can go back into the system. So there is some complex mathematical modeling going into the simulation of a qubit dissipating energy to an environment and then acquiring again this excitation. And finally, there is ongoing research on topological quantum circuit computing. And as you can see, this is a visualization of different gates that are applied to perform a computation. And in the future, quantum computing platforms will need to also take into account topological quantum computing. Finally, let me say that I would like to stress the fact that the success of QTIP and all of the other open source libraries in the quantum tech community, it's due to many of the features of Python and the excellently well-maintained libraries that are present in the Python ecosystem, which we use and we also thank. And also I would like to stress the fact that open source in quantum technology it's really affecting the way we are performing research, and this is something that I think many researchers can relate to. Thanks to publicly available tools, we can perform continuous integration, independent testing. We can self-generate documentation for the libraries and host them freely. And finally, we can publish our results using hosts like Zenodo, which also offer a DOI exactly at the time of publication, without waiting for peer review, for example, for data or articles. And finally, this is basically my last slide. I would just like to say that the quantum tech research community is really embracing open source, and there is a very active ecosystem of open source libraries performing different tasks in quantum research. For example, just let me point out OpenThermion by Google, an official Google project with also other universities worldwide and in the US, which allows to calculate chemical potentials for chemistry simulation. So finally, let me just give some future outlook for QTIP. We would like to implement GPU and machine learning with QTIP in a substantial way. This is already being done, but we would like to develop some modules. Shanawaz Ahmed is now starting a PhD on quantum machine learning, and he will still look after this part of research. We want to reach out, as I'm doing now, to the wider SciDev community in Python, and also nurture this nascent quantum tech community using Python or in general open source. We recently partnered with NumFocus, and from next year we'll have arrangements through Google Summer of Code. And we're also looking into using QTIP for control software as a software controlling actuators in quantum labs. Here, these are two meetings coming up that are also open to the bigger community of science developers beyond quantum physics. And here, this is just, I'm just highlighting the newsletter I'm writing. Here is, you can sign up here, and I've been writing some posts about open source in quantum tech, quantum machine learning, and some other topics related to technology transfer and research development in this field. Thank you very much.
Are there any questions? No? Okay, if not, then yeah, the next speaker can come up.
hello. So today I will talk about benchmarking and performance analysis for scientific Python. Myself, I have a background in computational plasma physics. I also contribute to open source software, in particular to scikit-learn lately. And at the moment, I'm working as an independent consultant for data science related topics. So, as was discussed previously in this conference, in the tutorials, there is a number of great tools for to make efficient scientific computing with Python, including NumPy, vectorization, Cyto, NumPy, etc. The question is, though, that before actually improving or optimizing our code, we need to measure its current performance and compare it to the new improvements. So in this talk, I'll focus on real-world cases, not micro benchmarks. And the question we'll try to answer is generally when we have some computational code or algorithm that has different solvers, which solver performs better, how does it scale, and how do we measure, which metric should we use to measure its efficiency in terms of, is it runtime, is memory important, etc. So let's start with runtime. So what are the ways to measure runtime in Python? So the easiest one is, like the most straightforward one is just called time, right? So we have a timer and then we make a difference and that's it. So the issue with this, one of the issues with this is that, for instance, on Windows, time is not the right timer, and that the precision is pretty bad. So which means that if we measure something which is fast, we will not get a good accuracy. In particular, timeit module exists in part to address these concerns. So it will, for instance, to sort an array, it will first repeat it several times, then time this execution, and then on top of that, we can repeat this numerous times to get some statistics. So this also has a lot of other things that are necessary to actually do good benchmarking. For instance, it will disable garbage collection, etc. So the issue, the limitation of this is that, how can we determine the number of repeats and number of iterations for a given code? And so that's probably why IPython Magic timeit is fairly popular, because it does that automatically. For instance, if you look at on popularity on GitHub, so it's debatable metric, but if you look in Python scripts, most of them are using time. There's some that are using timeit, and very, very few use the IPython Magic timeit. On the opposite, in Jupyter notebooks, the situation is opposite, and most of the notebooks that need to benchmark something, they use just the built-in timeit. So the reason this is it's a bit difficult to use the IPython Magic timeit is that essentially in a script, if you want to use it, you need to import IPython, create an instance, and then call something like IPython Magic timeit, etc. So this is not very straightforward. And if you do your benchmarks in scripts, that's not very nice. So some of these concerns were addressed by the perf package, which is essentially an improved version over the built-in Python timeit. However, there are still other questions that remain. In particular, how do we make parametric benchmarks? So, for instance, if we have, so essentially here we express our expression to be benchmarked as a string, and so if we want to parameterize it, it means that we need to pass some parameters inside the string. So either we do some string templating, or we define a separate function that we want to benchmark, and then somehow create partial functions of that function with different parameters. So it's not an easy question. And also the question is, how do we evaluate other metrics, such as memory or etc. And finally, we need a nice output, like a nice standardized format for results. So for instance, IPython prints the results to the standard output. That's not the way we usually analyze results, right? So in scientific Python. So if you want to do something more systematic, we need to write something up more. So to address some of these concerns, I've been working on a small side project, which essentially just wraps timeit and memory profiler to evaluate both runtime and memory usage. And the main difference with respect to for instance, the timeit module is that instead of writing expressions as string, we'll use delayed evaluation. So this is something that's strongly inspired by the way, for instance, JobLib or Dask works. So essentially, we have here we want to sort sorting of an NumPy array. So we create the NumPy array, we apply the delayed function on it, and then we sort it. We apply the sort attribute. Now this doesn't actually evaluate anything until we call the compute attribute. So the method, sorry. So for instance, this means that we can pass this expression without evaluating it to some evaluation function and do repeatedly evaluate it as many times as necessary. So this facilitates parametric benchmarks because it means that we can nicely just pass some parameter to sort or any other inside of this expression. So for instance, here's an example of parametric benchmarks. So we want to sort a vector of different size, and then we create this delayed object, we tag it with the size of the object, and then we apply the sort method. So now that we have generated these cases which don't evaluate yet, we will just pass this to the timeit function, and this will output a pandas data frame if we have pandas installed. So in the same way, if we, for instance, want to evaluate, get some statistics, we can just pass a few more parameters. So we'll get again a data frame with more information about it. Here it's aggregated by mean, max, and standard deviation. Or for instance, we can benchmark different metrics such as wall time, CPU time, and peak memory. And again, we will get data frame. So interesting here, the peak memory is 0, although actually the sort function returns the copy of the data at least. But what happens is that by default we use the memory profiler, and it samples with a frequency of 0.1 second, while the runtime here is below that value. So which means that essentially we need to adapt our peak memory measurement as a function of for instance, the wall time we measured. So it's essentially it's a fairly difficult problem. So let's take a short demo. How much time is left? Okay. So in this case, we will just want to, for instance, benchmark the logistic regression function from estimator from scikit-learn for different algorithms. So we'll initialize we'll initialize the x and the y vector, and what we will try to benchmark it with different solvers and with different number of samples. So the idea here is a bit of more complete benchmark. So when we run this, we get a progress bar, which is nice if you have a large number of benchmarks to know how long it will take. And essentially, because what we get is a pandas data frame, then we can use some of the. Okay, we have to wait for it. We can use the plotting ability of pandas to easily make essentially a plot. Okay, so here, for instance, you see the runtime for different solvers for logistic regression for the fit method. And what you see is as a number of sample increases, essentially the fastest one initially is linear, and then at later times is LBFGS. So of course you can make such a plot by yourself with just writing regular Python, but it can become a bit time-consuming to do it each time for different algorithms. So that's the reason for this, essentially, for this library. And the same way we can get the memory. So here's the memory usage for these different solvers. So of course, this is so far I have talked only about time and memory, but there's a lot of other metrics exposed by the OS. So I don't know if you saw these nice sketches by Julie Evans about what you can get from the proc directory on Linux. And generally, PSUtils is the package that exposes a lot of metrics in Python that is cross-platform. And so one of the objectives is try to integrate more of those metrics inside Neurtu to be able to benchmark them. So 2 minutes or? Yeah. Okay. So a small parenthesis on parallel performance. So essentially, this is an important part of like optimizing Python code. So often we do that, like sometimes we do that by looking at age-type output. So we look at whether all cores are used. But essentially, this is a bad way of actually measuring something because what we care about is just the runtime. So the much better way of doing it is just computing the strong scaling, meaning that we increase the computational resources and we measure the runtime for a fixed problem size. And of course, the results may strongly be impacted by, like, for instance, CPU frequency scheduling. So, for instance, in this case, single-threaded code may be actually faster for different reasons than parallel code. So this is something that we need to consider. In conclusion, okay, I'll skip this one. So in conclusion, Neurtu is a small package for parametric benchmarks, and there is a few different things that could be improved. For instance, we could estimate the memory complexities, time and memory complexities half automatically from like analytical expression of it. Use fixed computational budgets or support more of the PS skills metrics. That's it. Thank you.
Okay, thank you very much. I think we don't have any time for questions, so unless it's a very short question, if not, then you can ask afterwards, the break. Okay. Yeah. Now we'll have the next presentation.
Hello? Better. Okay, I want to start with a question like many others. Whom of you has contact with Fortran? Okay, some, and whom of you are using F2Py? And whom of you are cursing because you run into limits F2Py opposes? Yeah, okay, so maybe I can help you out. I have to admit my title is not completely correct. Right now there are some limitations of my new tool, F2X, but I'm extending it and developing it on it, and well, maybe I can find one or other user or even contributor. So first, some words about me. I'm from the German Aerospace Center. We're a big German research center with 8,000 employees, more than 8,000 employees, located in 20 locations with 39 institutes, headquarters located in Cologne, here. And we're doing research in the fields of space, obviously, energy, avionics, and also traffic. And yeah, there are some other fields like security, but it's not that clear. And of course, we are hiring always. And I'm located in Berlin, and part of the software engineering group. We help out different projects in different institutes, and I have a really broad history of scientific computing from HPC over some really data processing tools, and now currently I'm doing a really interesting project. So, but first, overview. I will give you first a short motivation about why writing a new wrapper, then some implementation details about F2X, some results and experiments I have, and in the end a short outlook. And first, my current project is about space debris. So there are lots of debris particles flying around in space, and they are really partly really critical because maybe some of you heard yesterday there was a hole in the ISS. This time it wasn't a debris particle, but it might have been. We are building up a catalog which surveys the lower Earth orbit, and we also have this catalog which then uses our survey data to predict possible collisions and stuff like this. And here's a nice picture how important it is. Like in 1 centimeter big particle with a speed of 14 kilometers per second can really do lots of harm, even if it's really, really small. And yeah, therefore we have partners in the German Space Operations Center, which help us develop this catalog, and they have a really cool flight dynamics software which is completely written in Fortran. And of course, we don't want to write our catalog system in Fortran, we want to use Python for different reasons, so we have to interact with this Fortran code. And yeah, okay, my first idea was, of course, use F2Py, and I looked at F2Py, and it's a pretty cool tool. It's really somehow the standard solution for wrapping Fortran to Python, and it's really in broad usage. It's stable, it's highly automated, and it's really easy to use for many cases. But our case is not simple. We don't use only primitives, but we really use modern Fortran 95 and Fortran 2008 features like derived data types, the Fortran structs. Yeah, the wrapper code F2Py generates is highly compiler dependent. We use a range of different compilers. Some of them are supported, some of them are not supported anymore because they are really old. Yeah, and so I started first looking into F2Py, whether I can extend it for derived data types, and I gave up this path after, I think, 2 or 3 days looking into the code and trying to extend it. And then there was another thing, F2Py is only supporting Python as target language. But in the beginning of the project, there was also the idea to wrap this Fortran code to C#, to Java, and to other languages, which are all in use in different projects as a German Space Operations Center. Yeah. So in the end, I started writing a new Fortran wrapper, and it pretty much looks like this. So this is a picture taken from my paper I just submitted yesterday to the PyHPC. So I hope it will get accepted. Otherwise, you can download it from the archive later on. So my idea is, so I have the Fortran source code. I have a small preprocessor, which makes the complex Fortran grammar a bit easier to digest. Then I have a Fortran parser, which generates an abstract generation tree. It's kind of an abstract syntax tree, but a bit shortened, only containing the relevant information to generate my wrapper code. And then I have a template-based wrapper generator, which takes a template, takes the AGT, and produces the wrapper code. And for every wrapping layer you need, you have your own template, which then produces a wrapper. So first, the parser. In contrast to F2Py, I use a real parser. It's not like I'm grabbing or taking regular expressions, but I really read the Fortran source code. For this, I use Ply+, which is a nice library which can really take grammars and BNF in Backus-Naur form and transform it into an ALR1 parser. But the problem is Fortran is not exactly ALR1 grammar, but a bit more complex. And the other thing is Ply+ is discontinued right now. There is a successor which should be more performant, but is not in my case. And yeah, so that's why it's a bit of a tragedy, but thanks to my design, the parser part can be replaced, and I'm looking for replacing it with an NLR parser. The grammar I use is thankfully borrowed from the Open Fortran project. They have a really nice and reduced grammar I could use. And in the end, I don't use an abstract tree, but the generation tree. For on the one hand, I wanted to decouple my generation part. As you can see here, I want to decouple this part from this part with a model which is more abstract than an abstract syntax tree I get from a special parser. And also, this helped streamlining the templates, because I only have to put things in the tree that I really need for generation. Yeah, as I said, I'm planning on incorporating NLR or other parser components. I'm looking for a student for doing this, but it's not that easy to find students which have enough background in compiler theory. So now the backend is template-based. As I already said, I use Ginger templates because they are really cool. They have nice text representation and can really not only support HTML, but any text format you want to use. The approach is taken from model-driven development, which is done in another department of my institute. And yeah, it's like you have a model, which in my case is the AGT, the abstract generation tree, and you have templates, and both together the model instance, so the AGT and the template are input, and out comes the source code for the wrapper. And that's pretty cool approach because this way I can really experiment with different templates for different approaches for wrapping. Like I have 3 or 4 approaches for exporting the Fortran features to C code, and then I have different templates which use this C code. For example, my C types template, which is currently the state of the art in my wrapper, but there's also some experiment with C# at the beginning. As I told, they thought about integrating it directly with C#, and there's also some experiments going on with using Cython for better integration. So in the end, what you get is you have your Python code, and now you have your Fortran code. I generate a bind C wrapper, which is really cool because this is a standardized way you can export your Fortran functions to C without being compiler specific. Then you can use these C interfaces from C types, for example. That's what I do currently, and then I can call it from Python. There's different templates available. Some of them were experimental, some of them are special for some projects, but yeah, you can extend it with special with extra templates for your special needs as you need. Here's a short example how it looks. This is a short Fortran code. So I have a function which takes some derived type. It's a polynomial. You have a degree, you have the coefficients. And from Python, you can really call it like it would be either from Fortran or if it would be really first-class Python citizens. And this is really executable in the end. So in DLR, as I already mentioned, it started from the project with the German Space Operations Center, and they actively use it since more than 1 year. And they were really helpful in finding bugs and extending features and pointing down features which are required. And yeah, they are currently building different wrappers, all with Python, but all using F2X, some directly accessing, some exposing web services or RPC interfaces. And it's used in production. So they really produce tools for their space operations that really use my tools. It's pretty cool, I must say. Well, I also run some benchmarks, and okay, it's not a big surprise. If you use C types for accessing C code from Python, you get really slow, especially if you have to deal with arrays or huge arrays. Then even if you use NumPy for the arrays, it's still a bit slow, but I had some experiments conducted with Cython. So there is the first preliminary Cython template, and it's on par with F2Py right now, partly even a bit faster. So that's for the state currently, and now some outlook. It's available under Apache 2.0 license. You can download it at GitHub. You can make push requests, and you can use it. The documentation is there. It should be enough to start working. Otherwise, contact me, and it will be improved, obviously. And yeah, currently I have support for lots of Fortran constructs, especially arrays, strings, derived types, arrays of derived types, array of strings are some features. And there are only 2 templates right now, the bind C template, obviously, for the exporting of the C interface, and the C types interface to consume it. But yeah, some implementations are also on my to-do list. So talking to different people here at the conference, I learned that callbacks will be very important to get people using my tool. Then I want better paths, I already told. My Cython idea was yesterday from the PyPy people improved to say, okay, better use CFFI. So my next template will be probably CFFI. And then I want also to integrate some automatic module compilation to make it as easy to use as F2Py currently is. So that's for it, what I have to say. And now I'm ready to take your questions if there's still some time, yeah.
Are there any questions? No questions? Okay, then thank you very much. Next.
Cool. Okay, so welcome everybody to my presentation about reproducible self-publishing via Python text, so Python and LaTeX. These slides, which we're going to see now, are basically a reference implementation of the technology. So they're made with the technology and they demonstrate the technology, meaning that in addition to listening to me, you might get the best understanding of what I'm talking about and also be able to reproduce it locally by cloning the repository. If you don't want to copy this, this link, I sent it to you all via Telegram, so you can just click it in the Telegram group. So let's get started. What do we actually want from free and open source publishing? What do we want publishing to look like? Well, we want a number of things. First of all, we want transparency. But I think it's very important to remember why exactly it is that we might want transparency. I mean, transparency and reproducibility have been hailed quite a bit these days, and rightly so. But I think it's important that we don't let these words become a sort of a mantra. Why do we need transparency? And the reason is we want research to be verifiable. You're trying to make statements about the real world, so you need to document what you did very precisely so that people can check it. Of course, you could do this by writing your method section very thoroughly, but why describe what you have done instead of just show what you have done? Verifying that something is true might work even better if you can rerun it, but that's like an asterisk. So transparency is what mainly provides verifiability. Reproducibility is something else which we totally want is there so that it can make things hackable. Basically, if things are transparent, you can check them for whether or not they're correct. Reproducibility becomes much more relevant, not for that, it just automates the checking, but for the case where you really want to be able to hack the work that's been done. That's where it becomes very relevant that you can run things locally in your own environment under your own control. I think thinking of this like that will help you avoid some of the common mistakes, such as using Docker as a package manager, which I know that very many people do. And of course, as we've heard in a previous talk today, a big advantage of publishing your publications as code as opposed to as binary documents is not just transparency, which means that you see everything that goes in them, and reproducibility, meaning that other people can compile them, but you also get all of the rich features which the Linux environment and the free and open source environment provide you for text files. So basically this becomes version manageable. You can diff your versions, you can blame your versions, you can collaborate much more efficiently with other people and also with your most important collaborator, which is you from half a year in the future. Of course, it's not just free and open source publishing, it's not just open source which we care about, it's also freedom. I mean, I hear about open science a lot. Very many people seem to forget the free aspect. And of course, we would like to publish in a distributed model where there's no central nexus where we have to aggregate things and where there's like a decision maker who lords over us, but where we can interact with each other in a completely flat distributed fashion. This removes the barrier of entry. You don't need your fancy credentials. You don't need a lot of money to publish, meaning citizen science can finally become a reality. It removes institutional bias. I mean, of course, we like to think that there's no such thing, but as you've seen also with Google and Facebook, platforms which share information might selectively censor information which they don't like. Thankfully, publishers deal in fact more than in opinion, but who knows, right? And of course, we would have less publication bias, simply because if you don't have to pay for the publication, it becomes less of a weird thing to expect of people to publish negative results. Because if publishing things just takes you one weekend, you're a lot more likely to publish something which you're not sure is going to be high impact than if a publication takes you a month, right? And of course, you get direct market access, meaning that you don't have to go through the publisher, which I'm going to get back to on the last slide. But the publisher used to be an enabler. Right now, like an enabler for you to communicate. But right now, the publisher more often is a barrier for your communication. And of course, you want to publish in a presentable format. And the presentable formats are fairly limited. These are articles, posters, and slides. Most prominently, notebooks are not presentable formats. They're optimized neither for presentable quality, so for high quality typesetting using the space efficiently, nor actually for development, as we've heard a couple of hours ago from Antonio, right? They're basically a runtime environment with very many interesting features, but they're neither well suited for publishing nor for development. So if you're looking to bring development and publishing together, the notebook might actually be a stopgap and not a format which it should converge on. So there's a lot of acumen regarding how you could integrate things so that they look nice for presentation, and all of that has been archived over years and years and years in the wonderful technology which we call tech. So it's best to leverage that technology to produce really beautiful documents with high resolution, which people can share and inspect, which people can print at high resolution, present at conferences, and basically get their information across a lot more beautifully and efficiently. So let's look at a couple of the features which I'm talking about, right? So the idea is to take Python code, simply link it inside the LaTeX document, not even write it in the LaTeX document, just link it and have the figures be produced directly in the LaTeX document. You don't need to copy them, you don't need to keep track of binary figures, but the code and the output is tied directly together, no stopgap. What could that look like? Well, you could have a 3D figure, which you don't export to anything. Basically, this 3D plot is generated each time this document is compiled, meaning that if I change anything about the figure, it's going to be updated the next time I recompile the document, without me having to save it, drag and drop it, copy it, or anything like that. The same goes for other figures. For instance, here you have a lot of nodes where you want to align the labels with the lines, and all of those stay in place. So basically, we leverage matplotlib very efficiently. We don't introduce any distortions when we place everything directly into the document. We can also plot some of the fancier figure types in matplotlib, anything you want, really. And of course, we can do the coolest thing about LaTeX. Anybody who's ever used LaTeX hates tables, but we can print a really nice book tabs, I think is the name of the package, style table directly from a pandas data frame, which eases a lot of your work in LaTeX in excess of just making it more streamlined and more reproducible. Yeah? You don't need to type the LaTeX table anymore. You just link it to your data frame. And of course, sometimes less is more. And I think the most revolutionary thing which we can do isn't even all of this, but it's this. And you might be like, okay, well, it's a line of text. I can write a line of text. I can type these things in. No, these are statistic outputs generated from a Python script, meaning that you can inline your statistics so that if you ever update your data, your top-level data from which the statistics get computed, this gets automatically updated in the text and in the figure at the same time when you recompile. The source code for all of these things looks fairly easy. So for instance, to put the radar plot inside the Python inside the text document, you simply have this line, which links the figure, adds a label, and can optionally add a caption. In order to create the table, you have basically this snippet of code, which again has a link to the script, which interprets the table, a label, a caption, options if you want to control the text size. So basically, the options just get inlined with the LaTeX code, and of course, the destination of your data. We're going to get to the data in a second. And for the statistics, you simply link the statistics analysis script, which in this case is an ANOVA. So how do all of these things integrate? Well, let's take a peek at the framework topology. Basically, if you've cloned the repository, you have all of that structure locally. What I'm showing you there is how the files relate conceptually, with the blue boxes representing the directory hierarchy. So the outmost box is the top level. Yeah? And basically, this structure helps you reduce duplication by only keeping the scripts in the same place. So you might want to have different formats, like you might want, based on the same scientific work which you're doing, to have a presentation, to have a poster, and to have an article. And ideally, if you're using the same scripts, you are linking the same scripts. You're not duplicating the code. And this is what happens here. So for instance, you have the top-level article tech file, which links to a header in its subdirectory where it keeps all of its things, such as styling and so on. And other sections might link to all of these scripts. The same thing could be true for the poster and, of course, for the slides. Ideally, you also wouldn't duplicate text content. So for instance, if you have the same abstract in the article and in the poster, you don't place it in their subdirectories, but you place it on the top level of the hierarchy. And the only bit which might look confusing is this part here with all of the lines. This is basically a many-to-many association. So you have these files can all link to all of the scripts. And of course, sometimes you might need data for the scripts to work on, and you have another data hierarchy which some of the scripts might call upon. Now the question is where you get your data. So what's the workflow behind this topology? And the workflow looks a bit like this, simply because very often, although you could trigger the entire process from compiling the LaTeX document, very often a lot of your work is very time intensive. So it won't actually help you work faster if each time you recompile your LaTeX document, you have to wait for 3 days, because that's how long it takes your pipeline to go from scratch. So to mitigate that, the workflow which I use for a number of projects where I need to do a lot of analysis work is to have this two-tiered system where I offload basically all of the time-consuming analysis to a separate iteration stack, yeah, which ends up generating a set of top-level data based on which I can do plots and statistics in the document. Yeah? So this is basically an asynchronous execution where I have low iteration for the time-consuming things and high iteration for the actual document with the absolute top-level analysis where I might want to tweak a lot of things and be very fancy about it. And if this seems like you've already heard this, it's because if I've counted correctly, there's at least 3 people who have presented something very similar this EuroSciPy. And I think that's a good sign. It shows that we're converging on a common solution. So ideally, we should try to establish this more if we already agree on this sort of organization and code to document tying. The last part is, of course, if you look here, you also have these dependency stacks because no software exists in the void. So you need to document what kind of things the software uses. And we also do this. If you've cloned the repository, we have a file which documents this. It basically specifies the compile time dependencies, which in this case there are none, and the runtime dependencies in a standardized format, which is the package manager standard. And this is because dependency resolution should be handled by a package manager. It should not be handled ad hoc by a bash script, which is basically what a Docker file is. So ideally, if you're unsure about package managers, you can pick one. There's very many of them, and you can use them. And whenever you have a project, you just have a file where you document the dependencies specifically for the package manager. And each RepSap iteration, so each publication, each collection of research project publications, which you would use RepSap for, should carry such a file inside. It doesn't need to be for the PMS, but I strongly recommend the PMS to anybody who's interested in package managers. So what does this mean for you specifically? Well, it means that you can co-author the reference implementation. I don't just talk about openness and transparency and flat structures and hierarchies. The presentation is written, but ideally we also want to publish this, not just in this distributed system, which we're trying to establish, but also in a more, how do you say it, in a more established journal in order to generate credibility for the project. But the article is not yet written. So the reference implementation at this moment only exists for the slides, not for the article. So you can contribute, or if you think you can do this a lot better than me, you can just clone it, fork it, and publish it yourself as the first co-author. This is what flat organization is all about, the best solution, making it through, not the guy who had the idea having a monopoly on the project forever. So if you want to contribute, you can contribute in any way you want just by going on GitHub. And of course, there's more. If you're really interested in research, you probably do research on the side. Like, I'm not trying to convince any of you to publish your real research primarily over RepSap because you're going to take a hit in credibility. I'm not encouraging anybody to torpedo their career that way. But if you have research which you can't publish because maybe you don't think it's quite serious or well elaborate enough, or you've done a questionnaire outside the university so you don't have the ethics committee stamp, which a lot of publishers require, you can use this technology to publish in a better and more advanced fashion your least exposed work. So you can use this to garner visibility for the things which in the current system are rendered least visible. When I was born, a researcher had no chance of getting to the public outside of the publisher system. That was your gateway to the world. Right now, as I said very often, they're a barrier because they have paywalls. Maybe you know some interesting things about the Elsevier logo. It's basically an elm tree with a vine growing on it, and the sense of it is the vine of knowledge, the fruits of knowledge can't stand on their own. It says here non solus, not alone. So they need the strong elm tree of the publisher to latch onto. Yeah? Another interesting thing about this logo is it's almost 400 years old, and it belongs to a company which is not Elsevier, meaning that Elsevier doesn't have copyright on it. They might have copyright on a lot of things, but not on this glyph which they use for their logo. So I think you know exactly where this is going. If pay for paywall has a logo, why shouldn't direct market access have one? And of course, we do. So thank you very much.
Thanks for a nice talk. Just an idea. Another way to interact with tech from Python would be to use the template engines like Jinja, which I usually use in web programming. And wouldn't it be possible to use more Python code and basically not even touch any LaTeX and use Python to generate basically text files?
So yeah, you could use Python to generate the text files, though I'm unsure whether you're saving more time that way, like basically by making a wrapper of text in Python.
I'm more comfortable with Python than with LaTeX, I have to say, or text. So
I mean, I'm very comfortable with both, but even I am more comfortable with Python than with Tech. However, I think that Tech won't get easier if you wrap it in Python than if you use it directly. I've made that experience with R and RPy. I mean, you can try to use that. As I said, fork and go. If your idea is better, it might get more citations. But I think that would be an additional step of complexity.
It's not my idea. I have seen people using it. So basically to automate the process of generating text files, basically.
Okay.
So,
yeah, I mean, to each his own. But for me, I think it's simpler this way. But everybody's welcome to use their own technology stack with this. Yeah.
okay. Thanks.
Yeah, I don't know if you are considering introducing some kind of a blockchain behind it, because it would be nice to have a publication which is a certified author with data and code and text fixed in time. So every time everybody knows where it's coming from, what it's about.
I've actually heard this suggestion a number of times, and I think it might be a very good idea. The only problem is I'm not very savvy in terms of blockchain and certification. But if you are, or if you know someone who is and who would like to contribute such a feature, I would definitely welcome it. Yeah.
One comment. Okay, one comment on that. It might not be necessary to go all blockchain. If you've gone to content addressing, you would have the verifiability. Basically, like Git is a content addressable system, and that might give you the properties that you actually care about, unless you care about like financial incentivization and all these other things that usually come with blockchain.
Yeah, I mean, I get the point. I think the entire financial part on top of this is a challenge. I mean, right now it's so easy to give things away. So I think the main challenge for the publication of the future is, one, establishing the technology, but two, somebody has to host all of these things and make some money. So at some point we'll have to figure out how to make money by giving things away. But I guess that's a bit getting ahead of the project.
Are there any more questions? If not, then thank you very much.
Thank you.
That's a great discussion.
Thank you.
You might have convinced me how I do my thesis when it gets there.
The thing is, I started this with my bachelor's thesis. It got even better at my master's thesis, and now I'm finishing my PhD, and I think I might have finally completely nailed it. So yeah.
That's great to hear that you've actually you put it through the
Yeah, I put it through, and all of my master's students basically now use this technology for their posters. So I wouldn't say that it's well established, but it's somewhat tested.
yeah, not just
It's not just me having coded something yesterday. Yeah.
yeah. I brought one more.
I don't know. I think they
Yeah, I think
bring it to the lost
people might be here.
Yeah.
Maybe someone whenever you want.
Yes, I guess this is just the next